Okay. Hello, hello, hello. Okay, let's get started. Let's see. Let me do this. Yeah. I think the bell just rung, and let's get started. Okay, so hopefully everyone had fun in 美足赛. And let's get a very quick review of last time. So last time we run over discrete time complex periodic complex exponential and discrete time periodic or harmonically related discrete time signals. Okay, so these are harmonically related discrete signals. So for those harmonically related signal, you have a common period n. And then just like continuous time, you found out that the harmonic related signals are often is e to a jk 2 pi over n and small n, and with k being integers. But for discrete time, we found out that this k only has big N different values that actually give you different signals. Because if the frequency of the discrete signal is too high, then because we are always sampling at the integer point, then we are just going back to the same signal. Okay? So those k are something from like 0 to big N minus 1. And also more generally, for periodic discrete signal, we found out that they are not always periodic. You need this omega 0 to be a rational multiple of 2 pi, then this only when this only when omega naught is the rational multiple of 2 pi, this e to the j omega 0 n will be periodic for a discrete signal, and then then you find out the rational ratio is small n over big N. Then if small n and big N are coprime, then big N will be the period for your periodic signal. Okay, so this is a very quick review of last time, and today we are going to a totally different topic. So let's not think too much about the review. Okay. So today, this is the main point of today. We are going to talk about the unit impulse function and the unit step function. There are 2 functions, or more like 4 functions, because they are discrete time version and the continuous time version. Okay, so those 4 functions are very useful because, well, when you multiply them to your signal, they give you some very intuitive signal processing you will get. Okay, but let's first see what are those functions. So it's a unit impulse and a unit step function. They are easier to describe in discrete time, so we start with the discrete version of the unit impulse function and the unit step function. And in the discrete version, you can really just write down the definition or draw them out. So the unit impulse function is a very simple function. It's almost like one of the simplest function possible. It's 0 everywhere. So it's, like I said, it's 0 everywhere, and except at n equal to 0, then it equal to 1. So you can kind of see why it's called an impulse, because it has an impulse at n equal to 0 here. Okay? So it's a unit impulse function, or called unit sample function. We'll see really soon that why it's called sample. But it's just this function that's 0 everywhere, and it has a 1 here. Okay. So that's the unit impulse function for discrete time. And also we would like to shift this impulse around like everywhere. So so we'll often do a time shift on this unit impulse function. That is, we just define this delta of n minus n naught n0. Then this impulse will shift it to the at this value at n0, and you can easily verify this by the time shift property we have done in homework, and also we can check again. So if you put n equal to n0 here, then it's delta of 0, so delta of 0 equal to 1. So this pulse should happen at n equal to n0. Okay, and this you can have delta n minus n0. Then you will have the unit impulse at n0 here. These are very simple function. And both this original version and the shifted version, we call them unit impulse function. Yeah. Function? No. Yeah. And the unit step function are a bit more complicated, but it's also very simple. So the unshifted version is this. So you can see why it's called a step. It's 0 when n less than 0, so whole bunch of 0 here, so it's constant 0 here. Then you pick up a step here at n equal to 0, and they become constant 1 when n is greater or equal to 0. So you can see it's like a step here. Okay. A step happening here. Yeah, so it's also a very simple function. It's O0 here and O1 here. And the step happen at n equal to 0. And also you can shift this around just like what you do in unit impulse. So instead of un, you have u of n minus n0, then this step will happen at n0 instead of happening at 0. Okay. Okay, so that's the definition, very clear and simple. Now, the next thing we want to talk about is there are relationship between just impulse and the step function. That's why we want to talk them together. Okay. And these 2 functions are really strongly related to each other, because you can kind of calculate one function from another. So the unit impulse function can be singled up as the difference between unit step function. So it's very simple here. So if you take this unit step function un and a shifted version u of n minus n minus 1. So the u of n minus 1 have step at 1. And you just take the difference, then you are left with the unit impulse function. Because for n less than 0, it's 0 minus 0 everywhere. And at n equal to 1, sorry, n less than 0, and n equal to 0, then it's 1 minus 0 equal to 1. And for n bigger than 0, then this is 1 minus 1 for over every n bigger than 0. So you see that everywhere else, this un and un minus 1 cancel out. And so you on the signal left over is just this impulse at n equal to 1. Okay. And just kind of like a differential and integration. So the impulse function is a difference between step function, and the step function will be the sum of impulse function. And this sum we actually this sum actually has we have 3 different ways to view this, and later on we don't actually use them, but it's still interesting to see them. So so let's see how this works out. Okay. So as we say, this unit step function can be written as the sum of unit step function. Okay, I guess. Well, anyway, let's look at this carefully now. And so we have a unit step function u of n, and then here we have a summation of unit impulse function. So we have delta of m. Okay, and it's a bit tricky here. Is you need to be careful about variables here. So on this difference equation, we only have n here, so everything is very nice. The delta of n and un minus un minus 1. Okay, but in this thing, because on this equation, then we have a HR dummy variable m that we need to sum over. Okay, so we have a delta of m here. Okay, and we are summing over m, and so we have a delta of m here, and now this axis is m, so we are kind of thinking we're summing over m. So we sum over, so kind of doing an integration for discrete time, so we sum over the signal at a different value. Okay, and so the summation is from minus infinity to n, and what happens is you are summing over, so from minus infinity, so this n from minus infinity, you sum to n is this u of n here. And you think whether your n is smaller than 0 or greater or equal to 0. If n is smaller than 0, then this summation never touches this actual impulse part, so this will be 0. Okay, so n equal to 0, this summation will be 0. And if n is greater or equal to 0, then this summation will sum over this delta of n part. You will sum over this impulse part, so you will get sum is 1 once. Okay, so it will be 1. Okay. And so this function, which is u of n, is 0 when n less than 0 and 1 when n greater or equal to 0. This is exactly the unit step function. Okay. So we see that the unit step function is the summation of m, delta of m, and from minus infinity to n. Okay. So this picture is, I guess, is one way to see the summation. Okay. Any questions so far? Once again, just to make sure the unit step function is like this: is 0 when it's n less than 0, and 1 when n is greater or equal to 0. Okay. So we see that we can write the unit step function on this rounding sum of unit impulse function. But this doesn't quite look like this summing over. So we have another picture. Okay. So the first picture of rounding summation, then we have second picture. Okay, the second picture, we start with this rounding summation here, and we do a change a variable. So basically what we want to do is we want to not having this n just on the range of summation. We kind of want this just like this equation. We kind of want this n as inside this function. Okay, and so we do a change of variable, and then we define k equal to n minus n. Okay, And yeah, so then we still write our unit state function as this unit sample function or unit impulse function. Okay. So if k equal to n minus m, then okay, then we need to write m as n and k. So n equal to n minus k is just move things around. Okay, so now we express m instead of n and k, m equal to n minus k, and okay, and then then n is from minus infinity to n. Now we want to sum over k. Okay, because okay, so we now sum instead of summing over m, we summing over k, and because n is just fixing, n is determined by this u of n here. Okay. So delta n minus k, and k from okay, and n is from minus infinity to n, and minus infinity m here become plus infinity k, and n equal to this is m equal to n, and when n equal to n, k equal to 0. So k is from infinity to 0. Okay. And so you see that if we do the change of variable, basically from m to k, then you have u of n is summation k from infinity to 0 and the delta n minus k. And summing over from infinity to 0 is really same as summing over from 0 to infinity. So, and yeah, so we say u of n is equal to k from 0 to infinity, delta of n minus k. Okay. And so this equation is pretty cool, although we will not really use it algebraically for too much for different things, but it's nice to see that. Nice way to see that unit impulse function, unit state function can be written as sum of unit impulse function. And I said there are 3 ways to see this rounding sum, and so actually we only have 2 equations, but this equation we have 2 interpretations. We can think of this kind of like a function of n or a function of k. Okay. And so here is the first picture. So if we think this equation as a function of n, then this will be kind of the reverse of this thing. Okay, and I think this is a more intuitive way to view this. So you are just thinking, well, if the delta of n is the difference over this unit state function, then this unit state function is really really the sum of this impulse at every time step. And yeah, so if you think both sides as a function of n, then you can have k equals 0. Then you have delta of you have just delta of n, right? So k equals 0, you have delta of n as this impulse here, and k equal to 1. Then as we know, k equal to 1, you shift you have delta n minus 1. Then you shift the impulse by 1 step. So this impulse here, this second impulse here, it corresponds to delta of n minus 1, and then. Then you can keep going at this, and k equal to 2, then you get this third impulse, because k equal to 2, you get delta of n minus 2, and that should be this impulse, and etc. going to infinity, k from 0 to infinity. So you see that this unit impulse function is this unit state function is really summation of those unit impulse function. This time shifted unit impulse function. So each value here is 1 impulse here. Okay, k from 0, k1, k2, k3, etc., all the way to k infinity. And finally, as the third way, we can also view this as a function of k, and then you will look at this. Okay. So we write this delta n minus k as a function of k, and actually delta n minus k you can easily verify, because the delta function is an even function. So delta n minus k equal to delta of k minus n. Okay, so this is the delta of k minus n. And so delta of k minus n, if you plot it as a function of k, then it's a unit impulse at n here. Okay, and then once again, you are thinking this kind of like integral. So you draw this picture as k here, and you have a delta of n minus k, or delta of k minus n at this n point here. Then the summation is from 0 to infinity. Then you see that if your n is less than 0, then your impulse is not inside this not inside this summation or integral area, and so this thing will be 0. And if k is greater, if n is greater or equal to 0, then your impulse is inside this 0 to infinity area. Then you get summation is 1 because you will sum over this impulse once. Okay, so that's the relationship between discrete time unit impulse function, discrete unit state function. Any questions so far? So yeah, there are a lot of ways to see this summation. Okay. And you kind of see this unit state function is the sum of a lot of impulse, and or you can see that you kind of integration over this unit impulse function, then you will get a unit state function because you get the integration area larger and larger, and at one point your integration area will go over through this unit impulse, and the integration will become O1 when it's over this, and it's O0 when it's not over this. Okay. And this picture is going to be important when we talk about continuous time unit impulse function. Okay. But anyway, then let's talk about kind of the application of a unit impulse function and unit state function. I think well, the more application part is for the unit impulse function. So what is unit impulse function really good for is when you multiply a function with a unit impulse function, then you can pick up the function value at some point, because it's really easy to see it as a picture. So you think about you have some whatever discrete function x of n here, and then you multiply it with the unit impulse function here. And then you see that for every n that's not equal to 0, you all become 0 because well, unit impulse function is 0 at all these points. So all those values got multiplied by 0 and become 0. Okay. So we write this multiplication. Okay, so this is point by point multiplication. When we write this x of n times delta of n is a function where its value at n is just x of n times delta of n. Okay. So this is a point by point multiplication of two functions. Okay, so if we do this multiplication, then for every n not equal to 0, the product here will be 0 because something times 0 is 0. And only at n equal to 0, you are multiplying x0 times 1, right? So at n equal to 0 is x of n times is x of 0. And so the resulting function is this, is 0 everywhere, and x of n at n equal to 0. And if you think a little more, then this function, x of 0 at n equal to 0. And if you think a little more, then this function is x of 0 times delta of n. Okay. So yeah, and so we should mark the really important part here. The really important part is you multiply x of n with delta of n, then you will pick up x of 0. You will still multiply by delta of n, and but anyway, you pick out x of 0 here. Okay, and so that's called a sampling or shifting property because you kind of sample out the x of 0 here. Well, it's multiplied by delta of n, but well, anyway, we have other way to process this signal later. For now, we we need to remember this property is really nice. X of n times delta of n equal to x of 0 times delta of n. And then more generally, if you want to pick up other value, if you don't want to pick up x of 0, you want to pick up some x of n0, then you just need to multiply your impulse function at a different point. Okay, so if you multiply your delta function at n some n0, so for example n0 equal to 5 here, then you will pick up x of 5 here. So the resulting product here will be x of 5 times delta of n minus 5. Okay. Any questions so far? No. Yeah. Okay. Okay. So I guess that's the easier part of today's lecture. Then we go to the hard part. Okay. So now things get confusing when we try to generalize this unit step function and the unit impulse function to continuous time. Okay. So what is unit step function? Unit step function is something that's 0 when n less than 0 and 1 when greater equal 1. Okay, so you can write unit step function kind of like this. But unit impulse function is something weird. So it's back to discrete time. So discrete time unit impulse is 1 at n equals to 0. But if you just have a 1 at n equals to 0 for a continuous time function, it's not very useful. Okay. So for a continuous time unit impulse function, it's a really funny looking thing. It's basically 0 everywhere, and it's infinity at n equal to 1, t equal to 0. Okay. Yeah. So it's 0 everywhere and infinity at t equals 0, and that's why we write this funny arrow here. This funny arrow here means that this function actually equal to infinity. Okay. Okay. So you see the funny arrow here. Okay. The function is actually infinity. And I guess before we go to detail here, that's easier to actually go to a definition. So how are the continuous time unit step function and the unit impulse function defined? They're actually not functions, they are limits of functions. Okay. And there are limits of those two functions. So we write this delta version of unit step and unit impulse. So this delta version of function, I guess there are actually two delta. So let's call triangle. Okay. There are triangle version of this unit step and the unit impulse. Okay. So those are functions well defined if you have a finite triangle here. So this u sub triangle function is just 0 when t equal less than 0, and 1 when t bigger than a triangle, and you just linearly interpolate. So you have this slope, very very high rate slope from 0 to 1 between this 0 and the triangle area. Okay, and similarly we can define a triangle version of this. So this delta sub triangle function. And it's a rectangular function. Okay, so it's 0 everywhere, and it has height. Height is really high. It's 1 over triangle, and width. So from 0 to triangle, it has height 1 over triangle. Okay, and what's important here is this area here. Okay, so what we really want is this rectangle. So it has height 1 over triangle and width triangle. So we want the area equal to 1 here. Okay, this is the most important part. Area equal to 1. Area. Wait. What? Oh. So this area equal to 1. 1. Area. Okay. Okay. So those two functions for every triangle, you can define that really nicely. Okay. So triangle is finite value. And we want to take those two functions and the limit of triangle goes to 0. Okay. And you can kind of, so now we are kind of going hand wavy. So the feeling you should get here is for the triangle going closer to 0, then the slope getting closer to a vertical line. Okay. And so u of t is the limit of triangle goes to 0 of this u sub triangle. And it will look like this. And then delta, and so this is kind of okay, except that it's undefined when t equal to 0. Okay, and there are different conventions you can take, but for now we just say when t equals 0, this function is undefined. Like some people will say u of 0 equal to 1/2. Some of them say it's 1. Some of them say it's 0. And anyway, let's just say it's undefined. So that's this part. And then this delta function, similarly, you want to take the limit of a triangle equal to 0 over the delta sub triangle. And now this is really funny, because this 1 over delta, 1 over triangle will go to infinity as triangle goes to 0. And the width will go to 0 as the triangle goes to 0. So you have this, so you really see this is impulse. So this is something that's really high and really sharp. So it has a 0 duration and infinite height. And but the important thing to remember is as this triangle goes to 0, the area always stays as 1. So I think this really high impulse is area 1 here. Okay, and this is the important part. And when we say 1 here, So we write this arrow and then we say 1 here, we really mean that the area has 1. The height is infinity, but the area is 1 here. Okay. And so we have some funny thing. We actually also define some k times infinity here. So we write the k times this delta function, k times this continuous time delta function. Then we can also have this k arrow here, means infinity, but the area is k. And as we'll see very soon, that this unimpulse function, they are really characterized by this area under this infinity height. Okay, so they are characterized by action of when you do integration over them. Okay. Question so far? No. So yeah. So anyway. So if you get really confused, then those are the definition of the unit step function and the unit impulse function for continuous time. And as we say, this is those are, if you go mathematically rigorous, then they are called distribution. And it's in particular for this unit impulse function, this is called a distribution instead of function. If you go mathematically rigorous, but that's not important for us. For now, we need to remember the area is 1 here. And also, there is something funny here for this taking limit thing. So taking a limit, the area always stays as 1, but something different happen. So, for example, this function, okay, so this function is not really an even function because as we define here, you see like on the right hand side it has some value, on the left hand side it's always 0. But when you take a limit, it actually becomes an even function or even distribution. Because, well, for every t bigger than 0 is 0, and for every t less than 0 is also 0. So we actually think delta of t equal to delta of minus t, even though delta of triangle not equal to delta of minus triangle. Okay. So this is something funny happen when you taking a limit. And yeah, so if you want to go a little further, so actually any function that kind of area 1 and kind of area 1 and the width going to 0, then the limit all goes to this unimpulse function. So what I'm saying is a delta of minus t is kind of like a limit of another. So you can kind of think of this delta of minus t. It will look like this function, right? So what it is a function that has a rectangular on the negative side. And I'm saying if you take this function and take the limit of the triangle go to 0, you also go to delta of t. Okay. And there are a lot of different functions that has their limit go to delta of t. And but they all have area 1 here. Okay. Question so far for the definition of unit impulse and unit step? No. And then okay. No question. Then one of the property you can see from to relate the unit step and the unit impulse is, well, from the triangle version you can easily verify that if you take a derivative of this triangle step, then it will become the triangle impulse because you take a derivative of this function. So for t less than 0 is constant, so it's 0. So for t bigger than triangle, then it's also 0. And between 0 and the triangle, the slope here is actually 1 over triangle. Okay. So delta of triangle equal to a derivative of u of triangle. And then if you take a you take a limit of triangle go to 0 on both sides, then we actually get that the delta function is the derivative of the unit step function. Okay. And yeah, and so something I forgot to say. So for unit impulse function of continuous time, a lot of time I will call it delta function. It's because one of the reasons is it's written as delta of t, and also this is more for the physics notation. Okay. So question.
What does the u with the subscript delta stand for? Does it stand for ut minus delta or?
Oh, this no. This is a triangle thing you are talking about, right?
Yeah.
So this means this function. So for every triangle, I define those two functions. Okay.
U with the subscript delta. Is
Yeah.
it any different from U t minus delta?
Yeah, it's very different. So U subscript delta is this function. So maybe write it bigger. So this is U subscript delta of t, and this is delta subscript delta of t. And you see this function that kind of is also kind of a step, but with finite slope. Right? It has a slope that it has a slope with slope delta 1/delta. Right? So yeah. so you see this is 0 here, so maybe it's a little too small here, so there's 0 here and the delta and the triangle here. So the triangle get the correct way is steep. Okay, so as triangle get smaller and smaller, then this slope here will get steeper and steeper. Okay, and so maybe I can just write a comparison. So if you want, what you were saying was u of t minus delta, right? T minus triangle, then that function is a time shift of this function, and that will just look like, let's say the triangle is positive, then it will just look like this, right? And this is a triangle. Okay, so there are different functions, and why is this not drawing? What? Anyway, yeah. Okay. Any other question? So those are the definitions of continuous time unit step and unit impulse function. Okay, maybe I'll just erase this. Okay, and the relation. So we kind of go to a second equation first, second relation first. So the unit impulse function is the derivative of the unit step function. Okay, so you kind of think about this as this infinite jump. Then you take a derivative, then it becomes this infinite derivative here. And you can think of that as the limit of this function taking derivative becomes this function. Okay. Okay. So these two equations are actually very important both. So the delta function is for continuous time delta function is the derivative of the continuous time unit step function. And so that's a derivative, and as we know, you take the integration of derivative, then you get back the same function. So integral is the inverse of derivative. And from just this equation, then you can derive this equation. So the unit step function is the integration of the unit impulse function. And the integration area is minus infinity to t delta of tau d tau. Okay. And you can view this as this picture. So it's similar to a discrete picture. So if you write this tau, so we picture this as a dummy variable tau here. Okay, so it's a tau here. So you have impulse at tau equal to 0 here. And you're thinking about you increase the integration area. So integration from minus infinity to t. And if t is less than 0, then you are integrating over constant 0. So the integration should be 0. And then if integration this t is bigger than 0, then you integrate over this unit impulse here. And as we say, this unit impulse it has area 1. So when your integration area is over this unit impulse here, then the integration should be 1. Okay. So when t less than 0, you got 0. When t bigger than 0, you got 1. And that's exactly our unit step. And as we said, the unit impulse function is really defined by its integration. So you can view this rounding integral as as an alternative definition of your unit impulse function. Okay, and you can see that The property of this unimpose function is really fun. It has no duration, so everything happens at this really sharp t equal to 0, and the pi has a uni area. It's important to remember that the area when you integration over it has area 1. Okay, and yeah, that's the round integral and the first derivative. They are somehow, in my view, more important than the discrete time version. But you can kind of remember them as the generalization of the discrete time version. Okay, any question? Oh, yeah.
So what is the duration?
Duration, oh, it's 0. Oh, I guess the duration, yeah. Duration of signal is kind of like the length of the non-zero part. Okay. I guess we haven't defined duration yet, but I can draw a schematic. So sometimes the signal, because our signal are a lot of times they are physically motivated, so we'll think of our signal happen at some time and stop at some time, and this interval will be like a duration. Okay, yeah, and yeah. So you see for the unit impulse, the signal happen at this really sharp impulse at 0, so the duration kind of 0. Okay. Okay. And yeah, that's the relationship. And then similarly, we will want to do a change of variable on this rounding integral and view this as a different picture. Okay, so we have this rounding integral, and we can do change of variable. So once again, we change from tau to some sigma equal to this t minus tau. Okay, so the thing to check here is where we put t. Okay, so t here and t here, and then want to put t down back down to the variable here. Okay, so u of t and the delta of t. So anyway, we do change of variable and change of variable, and let's do this carefully. And tau sigma equal to t minus tau. So tau equal to t minus sigma here, and d tau. We are doing integration instead of summation, so we have a bit difference. So d tau equal to minus d sigma, because the t is kind of constant, so d tau equal to minus d sigma here, and then integration area when tau equal to minus infinity, then sigma equal to minus infinity equal to plus infinity, and so this is similar to discrete time. So when tau equal to t, then sigma equal to t minus t, and so we got 0 here. So u of t equal to plus infinity to 0, delta of t minus sigma minus d sigma. And this minus sign you can move to this change of integration order. So the minus sign changes infinity to 0 to 0 to infinity. So u of t equal to integration 0 to infinity, delta of t minus sigma d sigma. Okay. And once again, you can view this as two different interpretations. And so one of them is kind of like a discrete time summation. So we think of this as a function of t, this as a function of t. Then this is less intuitive than a discrete time. So discrete time, we say you have a whole bunch of inputs listing together, then it becomes a unit state function. But you see that this doesn't really quite work in continuous time, because the continuous time all of those delta of t minus sigma, they are impulses they are infinite impulse at a different sigma value. Okay, so it's kind of hard to picture that you have a whole bunch of really sharp impulses together and merge them together into a unit state function. But anyway, this is mathematically correct. Okay, and then another way to view this is another way to view this is you think of this as a function of sigma. Okay. So I put this. Okay. So you put this as a function of sigma, and just as before, we say that delta function is an even function. So delta of t minus sigma is delta of sigma minus t, and so this delta of t minus sigma is a unit impulse function shifted to t. Okay, And then you can think about this integration of sigma from 0 to infinity. Then when t is less than 0, it's not inside this integration area, and when t is bigger than 0, it's inside the integration area. And so t greater than 0, this is 1. Okay? Question? Okay. So yeah, I guess at a very high level, remember that a unit step function is an integration of a delta function, and delta function is the derivative of the unit step function. Okay, and then similar to discrete time, we go to this shifting part. And for the shifting part, now this is a bit more hand waving now. Okay. But what we want is we still want to shift out the x value at some point. Okay, so we think about what is x of t times delta of t. Okay, and the derivation we kind of go back to this delta subtriangle. Okay, so we think about x of t times this delta of triangle function. So this delta subtriangle function, it only has a value between 0 and the triangle, and it has really some height triangle going higher and higher. Okay. And so we are thinking when we so we want to take this value, and so we want to think about this value and take a limit of triangle to 0. So triangle becomes really small. And what happens is when triangle is very small, and your x of t is kind of nice, it's smooth. Then as the triangle getting smaller and smaller, the x of t between the 0 and the triangle value get flatter and flatter, right? Because if x of t has some finite derivative, then x of 0 and x of triangle should be about the same value. Okay, so at this point, so what happened is, so at this point, this is x of 0. Okay. So the x function will be x of 0 here, and it will be x of triangle here. And we think that if triangle is very small, then x of 0 is about the same as x of triangle. Okay. And okay. And so you think about the product of this function is delta subtriangle the x of t. Then just like the discrete time, when t is outside of this 0 in the triangle, so when t is less than 0 or bigger than the triangle, it's all 0 because delta subtriangle is 0 outside there. And inside, then it's obviously this delta subtriangle is 1 over triangle thing. It's really high, and times some x function between 0 and the triangle. And then we think that x has some finite derivative. So between 0 and the triangle is actually about x over 0. Okay, because x of the triangle is about x over 0. And then we have this very hand-wavy derivation saying that as you take the triangle goes to 0, then this product actually becomes just x over 0 times delta of t, times delta of triangle equal to delta of t. Okay. So this is a shifting property we have. I guess I should give it a frame here. And yeah, so this is a shifting property for the continuous time function, x of t times delta of t. So just like discrete time version equal to x of 0 delta of t. And then similarly, if you want to pick up x of t at a different value, so say you want to pick up some t0, then you just multiply this delta of t minus t0. And maybe I should draw a picture here. The delta of t minus t0 will be imposed at t equals 0. So this will be like this. Okay. So t0. Okay. And t. Okay. And delta of t minus t0. So delta of t minus t0. Anyway, yeah, delta of t minus t0 will have an impulse at t0. And when you multiply any function x of t with delta of t minus t0, then the function value at t0 will get picked up, and this have delta of t minus t0 here. Okay? So in summary, those are the shifting property for continuous time function. X of t times delta of t equals x of 0 delta of t. And x of t times delta of t minus t0 equal to delta of x of t0 got picked up. And this delta of t minus t0. Okay, question. Not, then we have 3 minutes to go to this example. Once again, I have wolf text, but I think we can do this fairly quickly. So we have this funny function. Look at this. It's some piecewise constant function from 0. So it's constant 0 on here, constant 2 here, and constant minus 1 here, and constant 1 here. And they want to take a derivative of this. And so we look at this function, we realize it's really like a lot of unit state function piece adding together. And so what happens is when you take a derivative of them, you pick up a whole bunch of unit impulse function. Okay, pick up a whole bunch of unit impulse function. So for example, on this jump from 0 to 2, so it's like twice of unit state function happening here. And when you take a derivative here, so remember delta function is a derivative of unit state function. So the jump happening at t equal to 1 here is like a unit state function with height 2 here. And when you take a derivative, then you just get twice of a unit impulse function. So yeah, so when you take derivative here, you get 2 here. And then it becomes constant once again, so it's constant between 1 and 2. So take derivative is 0. And so similarly, at t equal to 2 here, you get a unit state jump from 2 to minus 1. So it's a minus 3 jump here. So when you take derivative here, you get a minus 3 unit impulse here. And finally, when you take derivative at t equal to 4 here, it's a jump from minus 1 to 1. And so that's once again a 2 unit impulse function here. Okay. And we have 1 more minute, so I guess let's finish this. Okay. So basically, we use this thing to get the derivative of this function, because so it's a constant basically everywhere, but it has a 3 discontinuous jump. So the 3 discontinuous jump is like a jump in the unit state function. And if the height is 2, then you get twice of unit impulse, okay, etc. And then you can check that you have those 3 impulses here, and you take the integration, you will get back this function. So the integration is kind of interesting. So you think about integrate from minus infinity to t. So before you hit this impulse, then the integration is all 0. And when you go integration over this impulse at t equal to 1, then you get height 2 here. So you got this jump to 2. So integration value become 2 here. Then similarly, then you increase your integration area even more. So integration area is over this 2 here. Then you additionally get this negative 3 area, right? Remember, the impulse function are all defined by these areas here. So we go over t equal to 2, you get this negative 3, so you get a negative 3 jump. And similarly, when you integration even more, when you go over 4, then you get this plus 2 jump, plus 2 area jump. So then you got this plus 2 jump here. Okay. Yeah, and here are things right on an equation, you can read yourself. And yeah, so I guess that's it for today, and I will see you on Friday. Friday we should finish chapter 1 and start on chapter 2. Okay, yeah, see you on Friday.